In this video, we are going to work on using index notation in order to prove differential operator identities. We will review the Einstein summation convention, the dot product in Kronecker-Delta, the cross product in Levi Civita, and then we'll use these to do some proofs on differential operators. The first one here is to show that the divergence of the gradient of f is equal to this del squared operator, which is the Laplace operator on our vector field phi. The other example we will look at involves looking at the curl of a vector field. And finally, our final example will look at the divergence of the curl of a vector field and show it is equal to 0. Before we get into the main part of our video, I'm going to tell you that this is not one of my favorite topics. However, I will concede it is extremely useful because if you need to prove these identities, especially, you're proving them in general and not just showing it for one particular vector field or phi. If you want to show it in general and you have anything that's any degree complicated, like when you start a curl of a curl or you have this Laplace transform, your calculations, if you just write your phi as, a phi 1, phi 2, phi 3 of x, y, z, it'll get really unwieldy really quickly, and this is the way to go. First, we'll do a quick review of things we talked about, I think, in our first video. The first thing is the Einstein summation convention. So if you have a term that has repeated indices, it is understood that this is a summation. We're summing over the indices. So v sub I, e sub I is understood to be the sum for I equal 1 to 3. It could actually be more, but usually we're working in 3 dimensions. V sub I, e sub I. So that would be v1, e1 plus v2, e2 plus v3, e3. The next thing we want to talk about is the dot product and the Kronecker-Delta. So in index notation, we define a dot b, or we found that a dot b is equal to a sub I, b sub j, this Kronecker-Delta sub ij. The Kronecker-Delta is equal to 1 when I is equal to j, and 0 when I is not equal to j. So what that means is everything, if I does not equal to j, it's going to be 0. So that means the only components that are going to be left are the ones where a sub I is, and when we have the ith component of A and the ith component of B, and then we can get rid of the Kronecker-Delta. We use the Levi Civita here to help us with the cross product and notation indice. And we did in the first video the cross product and showed that this definition of the Levi Civita will give us the plus or minus signs when we do all the determinants, when we do cross products. So that's what this is about. In index notation, A cross B is A sub I times B sub j, and that will give us our kth component. So we multiply by the kth basis vector, and we multiply then for the -1 or 1 or 0 by the Levi Civita I, j, and k. And I'm sorry, I used to call it Levi Civita, but then now it seems like everyone calls it Levi Civita, so I'm trying to change it. So anyway, multiplied by the Levi Civita I, j, and k. And you'll notice the indices. So this I comes from the indice of our first matrix, the j comes from the indice of our second matrix, and the k comes from which component of A cross B we're looking at. So eventually, you can actually even just drop this E sub k because it's understood from this Levi Civita. The other thing about the Levi Civita is we can convert two Levi Civitas that have one index in common to Kronecker-Delta. It's important that the index is at the end, but it's not a big deal because we can notice from here, and we showed this in our first video, that we can kind of rearrange or permute these indices. So if we swap two indices positions, so for example, if we swap j and k so that ijk becomes ikj, it's the same number except negative. If we do another swap of two, from here, two more, then we'll have another negative sign. So even swaps preserve the same number. Odd swaps give you a negative. So that was our quick overview, so now we're ready to do some proofs. Our first example is to show that the divergence of the gradient is equal to this del squared phi, and the del squared is the Laplace operator given to us in notation, index notation over here. For the del operator, I'm going to use this index notation. That's the e sub I, the ith vector, direction vector, times partial derivative with respect to x sub I. So now I can look at my del dot, or my divergence, but my del dot the gradient. So I'm going to plug in e sub I partial derivative with respect to x sub I for del, and I'm going to dot it then with my notation for gradient, which is e sub j, then partial derivative of phi with respect to x sub j. Next, I'm going to group my direction vectors, so I have e sub I, e sub j, then I have my partial derivative with respect to x sub I times partial derivative of phi with respect to x sub j. Since direction basis vectors are orthogonal, they'll be equal to 0 if I does not equal to j, and they're equal to 1 if I equals j. So what I'm going to do then is this e sub I times e sub j, that's essentially the Kronecker-Delta, or not even essentially, that is the Kronecker-Delta, delta sub ij, and then I have this other factor brought down here. And as I had mentioned, when you have this Kronecker-Delta, that means these indices must be equal, and then we can get rid of the Kronecker-Delta. So we have partial derivative with respect to x of I. We change this j to an I. We have partial derivative with respect to x of I of phi. So we take the partial derivative of phi with respect to x of I twice. So it's like d2 dx1, d2 dx2, d2 dx3 of phi, which is simply the gradient squared, or the Laplace operator, times phi. And that's exactly what we wanted to prove, that the divergence of the gradient is equal to the Laplace operator on phi. So we take the partial derivative with respect to x sub I, and then we take the partial derivative with respect to x sub I again. So here we have our summation. We're essentially taking d2 dx1, d2 dx2, d2 dx3 of phi, which is the Laplace operator over here. We have our Laplace operator defined here of phi. So we have proven, now if we look at this equation, we've proven that the divergence of the gradient of phi is equal to the Laplace operator of phi. Our next example is the identity, the curl of a vector is equal to del times the divergence of the vector minus del squared, which is the Laplace operator times v. I have for your reference the Laplace operator written in notation here, as well as the del operator written in index notation, and I have the Levi Civita notation here for your reference. I've copied my curl of the curl here, and the first thing I'm going to do is expand this cross product using the Levi Civita notation. So what I notice is that when I have A cross B, so this is del cross V, so A is del, B is V. If I take A sub I and B sub j, and then I have my kth vector. So this is the kth component of A cross B, multiplied by my Levi Civita, my I, j, and k. So here, because I wanted to match the indices in your book, I'm going to take the rth component of my del, the s component of my v, so I have these two. Then I need another, my directional component, and I'm going to take the jth component, and then I have the Levi Civita, I, j, k. So here I'm going to have r, s, and j. So this here comes directly from this definition of the cross product. I just used different indices. Instead of I used r. Instead of j, I used s. Instead of k, I used j. And then you can see the Levi Civita is I, j, k here. So we need R, S, and J. And again, I chose the R, the S, and the J because I wanted to match the notation that your book is using. And this next step, all I did is I said, well, the rth component of the del operator is d dx dr. To go from here to here, what I'm using is the fact, let me look at this definition of the cross product. This E sub k is going to pick out the kth component of the cross product. And it's reflected in this Levi Civita because you have A sub I, B sub j, the k tells you what component is being picked out. So in other words, in this notation here, when I have d dxr, the rth component of my del, and then I have vs, that's my s component of v, then I'm going to have my E sub j, so I know I'm in the jth component, but my Levi Civita already tells me this is the jth component. So I can just drop this j, and then it's understood that this is the jth component. So from this line to this line right now, this is just a direct copy of this. My del cross, my dx, my partial derivative with respect to x in the rth component, my vs, my ej, my Levi Civita, rsj. So what I'm going to do is I'm going to get rid of this ej because it's understood, and we understand now, and this is important, that this is the jth component of this cross product here. And what I'm going to do now is apply this cross product formula again. So I'm going to get my del sub I, that's like my A sub I. Over here, I already have my jth component. That's my d dx sub r, vs, Levi Civita, rsj. That's rs, and it's the jth component. And then, so this is the ith component, this is the jth. So then I'm going to put my kth direction vector, and my Levi Civita is going to be my I, this is my j, and then my k. So this is the kth component. And like I did previously for this, this del sub I, I'm going to convert it to partial derivative with respect to x sub I. So now I have d dx sub I, d dx sub r, vs, epsilon rsj, e, the kth direction vector, and epsilon ijk. And what I see here to simplify is I have these two Levi Civitas, and they both have a j index, which is good news because if you have one of the indices equal, you can use this this identity here. The problem is it has to be the last indice that's equal, but that's okay because if you recall over here, if I just permute these symbols an odd number of times, it's equal to the same constant except negative. If I permute them an even number of times, then they're equal. So here, if I just permute the j and k so that I have I, k, j, I will have the j at the end. I can use this property, but I need to add a negative sign. And actually, before I did that, I did kind of combine some of these things. I have my partial derivative with respect to x sub I. I combined this partial derivative with my v sub s, and I moved my e sub k over here. I put my Levi Civita symbols together here. And now, to get the j to the end so that I can use this property here, I need to permute the j and k, so I switched their order. That was one switch that got the j to the end, so it's an odd number, so I need to multiply everything by a negative. The next thing I can do now is use my property to convert this Levi Civita symbols, or two Levi Civita symbols, into these Kronecker-Delta symbols. So what I do is, for the first two Kronecker-Deltas, I take the first symbols from my Levi Civitas, the I and L, and then I take the second symbols, J and M. So that's what I'm going to do here. My first symbols are R and I for my first delta Kronecker-Delta, and then I take the second, S and K. for the part that comes after the minus sign, I take the first and second, that gives me IM, and then I take the second and first. That will give me the JL. So over here, I'm going to take the first and second, that gives me RK, and then I'm going to take the second and first, and that gives me SI. So this here has converted these Levi Civitas into Kronecker-Deltas. These Kronecker-Deltas are just scalars, and actually they're just zeros and ones, so I can distribute them. So I'm going to distribute this here, so I get my partial derivative with respect to xi, and there's a negative sign, my partial derivative of vs with respect to x bar, my ek, then I have my Kronecker-Delta ri, Kronecker-Delta sk over here. Similarly, I distribute here, the two negatives give me a positive, my partial derivative with respect to x bi, my vs xr, my ek, and then my Kronecker-Delta rk, Kronecker-Delta si. This Kronecker-Delta says that r must equal to I, so I'm going to convert this r to an I. This Kronecker-Delta says that s can equal k, so I'm going to convert, what am I going to convert? My s here to a k. So I've done that here. So my r was converted to an I, my s was converted to a k. Over here, I have that r can be converted to a k. So I'm going to convert this r to a k, and then my s over here I'll convert to an I. I move some things around. I put this basis vector next to my vk. I move this basis vector in front. And then the other thing, this is partial derivative with respect to x sub I, and then we have the partial derivative with respect to x sub k. But it doesn't matter what order we do that in vector calc, right? When you do partial with respect to x and then partial with respect to y, you can do it the other direction, partial with respect to y, then partial with respect to x. So I did the k first and the x sub I later because I wanted to group my i's together here. And now finally, I take this and I convert it back to vector symbols. So over here, if you look and you compare this to the definition here, my ddxi, my ddxi, that's my double gradient or my Laplace operator with a negative sign times v. Over here, I have my dvi, dxi, so I have my dot product, and then I have my del times my dot product. So I have proven this identity here. I have one more example, which is to prove the divergence of the curl of a vector field is 0. So that's in symbols the divergence, so del dot, and then the curl, del cross A equals 0. I start by expanding this cross product using my Levi Civita. So my first term, or my first vector, I'm going to take the ith vector, the ith component. My second vector, I'm going to take the jth component. I'm going to multiply by the kth basis vector and the Levi Civita ijk. So this is the cross product, just plugging it into this Levi Civita formula. The next thing I'm going to do is replace this del operator, the ith component of the del operator, with partial derivative with respect to x sub I. Over here, what I've done is when I look at this notation, this Levi Civita ijk, the k over here tells us which component it is because we multiply by the kth basis vector. So I'm just going to take away the kth basis vector and let my Levi Civita tell me I'm in the k direction. Now I'm going to do this del operator dotted with this kth component here of the cross product. So my del operator is a sub I times b sub j delta sub I, the Kronecker-Delta sub ij. So I can't reuse I for this del because I've already used it for my this del over here. So I'm just going to use the index r. So partial derivative with respect to r. This is, again, the kth component. So my Kronecker-Delta is going to be r and k. And this tells me now with the Kronecker-Delta, I can get rid of it if I replace my r subscripts with K. Or I could do K with R, but it makes sense to do replace R with K. So I'm going to replace this R with K, and I'm getting rid of my Kronecker-Delta. So I have partial derivative with respect to K, x of K, partial derivative with respect to x sub I, my A sub j, my Levi Civita, I, j, and k. There are two things I did in this next step. The first is the Levi Civita, it's just a constant. So, right, it's either equal to 1, -1, or 0. So I can move it out in front. The next thing is I have two partial derivatives, first with respect to k and next with respect to I. And if you recall from vector calculus over here, that if you take a second order partial derivative with respect to x and y, it's equal to the second order partial derivative with respect to y and x. And for whatever reason, I wanted the dx sub I first and the dx of k, probably because I was going in alphabetical order, but it doesn't matter. I could have written dx of k, dx of I, a sub j. This step here looks kind of strange, but what I did is I wanted to swap my I and k. So here I called my I equal to k and k equal to I. So I just renamed my indices. So I renamed I to k and k to I. I left j to stay the same. So here I have the second order partial derivative. I renamed I to k and I renamed this k to I. My j stayed the same. And this is a strange thing to do, but you'll see in the next step. So what I do is I have this expression here, my Levi Civita I j k second order partial derivative with respect to I with respect to k, a sub j. Well, that's equal to 1/2, and then I add these two together since they're equal. So it should be equal to this over here. Now, if I look at my indices here, my Levi Civita I, j, and k, if I swap these two indices, just permute the j and k, I have to put a negative sign. So I have the epsilon ikj. Now I'm going to permute the I and k. So I have epsilon k ij, but I need to put another negative sign, and then I'm going to permute the I and the j. So I have that's equal to negative the epsilon Levi Civita kji, which is this term here. So this here, this is if epsilon of ijk is equal to 1, this epsilon of kji is equal to -1. Remember, these two things from vector calculus are equal, which means this expression here is equal to 0, which means our dot product of the cross product is equal to 0. To review what we've covered in this video, first we reviewed the Einstein summation convention, the dot product and Kronecker-Delta, as well as the cross product and the Levi Civita notation. So for the Einstein summation, what we said is when we have this repeated indice, it's understood that that means we're summing over that indice. The dot product, we can put in this indice notation, and also when we multiply by the Kronecker-Delta sub ij, what that means is these two need to be equal, so we can convert them both to the same indice and then get rid of the Kronecker-Delta. A quick review of what we covered in this video. We talked about Einstein's summation convention, which was if we have a repeated indice, it's understood that we sum over them. We talked about the dot product and the Kronecker-Delta. So the dot product was defined as a sub I, b sub j, this Kronecker-Delta ij. So the Kronecker-Delta means that it's 0 if I doesn't equal j and 1 if they're equal. So we can change this Kronecker-Delta means these two indices can be the same, and then we can drop the Kronecker-Delta. We did the cross product and the Levi Civita. So a cross b is equal to a sub I times b sub j, and then we multiply by the kth direction vector. So this e sub k gives you the kth component, and then we multiply by the Levi Civita ijk. You notice the I follows the A, the first matrices index, the J follows the second matrices index, and the K tells you which component you're going for. We have these couple of identities that we also used, and then we used these things here in order to prove identities for our differential operator. This was the first example we did, and we did one other example. So that's it for this video. Thank you for watching.